Whose life would be better if you knew more C++? Whose life would be better if your coworkers knew more C++? Let's get started.
All right. Hey, everybody. Welcome to CppCon in the Back to Basics track. I'm Brian Ruth, and today we're going to talk about casting, or subverting the type system. So first, an introduction. A lot of times people see casts as a way to deal with warnings that you may get. Somebody has the warning level turned all the way up. You're writing this code, you're comparing a buffer size to an integer, and you're like, well, the buffer size is always going to be smaller than the integer, so this should be fine. So I'm just going to throw in a cast, and the compiler warning goes away, and we're all good to go, right? Except years later, someone realizes that int size is not initialized to anything. So I'm going to make it an invalid size. It's an int, invalid size is -1, and we still have our cast there. All of a sudden, that turns invalid size into a huge number. So it's not doing what you expect it to do, but you're not going to get any warnings because you told the casting system, you told the type system, no, this is fine, convert it to a size t. From Design and Evolution, which has come up, this book is a great book. It's got a huge section on casting that I highly recommend you read. But from that book, he ended this section on casting with, in all cases, it would be better if the cast, new or old, could be eliminated. Unfortunately,
you want questions, help me.
Well, you could go ahead and ask it now since you got my attention.
Design and Evolution, it's on a print, right? How do we get a copy?
So the question was, how do we get a copy of Design and Evolution? You can get them on eBay, you can get them, I got mine used on Amazon, like they exist and they're not overly expensive. So that has nothing to do with casting, but so anyway. But why do we need casts? So why couldn't we get rid of casts entirely? Well, C++ is a statically typed language. And since C++ is also a system language, we need a way to work with raw memory. And because it's also an object-oriented language, we need a way to navigate up and down that inheritance hierarchy. The thing to remember about casting is it is all about the bits. So what is a type? Let's say we have these bytes just in memory. What does this actually mean? Well, it could be 2 integers with these values, or a double with that value, or 2 floats, or a size t, a struct with 2 member values and 2 of those back to back, or it can be a string that says CppCon. It can be anything. So I'm going to talk a little bit about automatic type conversions that the compiler do for you. It's not the purpose of this talk, but a little bit of background is going to be useful for understanding what's going on with casting. So automatic conversions, it essentially allows the compiler to perform a sequence of operations to convert one type to another without you explicitly telling the compiler to do it. So a good example is the normal implicit type conversion. So here we've got a float that we're assigning a value to it. Well, a literal like that is actually a double. So when you assign that to the float, it actually does a little bit of conversion and the memory representation is a little bit different. So the value assigned isn't exactly the value that ends up in that float. And you can take that float and assign it back to a double, which changes the value again. But you never really had to tell it to do anything. You can assign the float to an int. You can assign it to a size t, and it does a conversion. You can assign it to a character, and it'll turn it into something. And it can even look through your code to create objects based on this implicit conversion. Another one that kind of catches people by surprise is arithmetic type conversion. There's a whole list of stuff. You can go to that link and it shows all the different ways that things get promoted and stuff. But it kind of messes with people a bit because you would think here, I have a function that takes 2 8-bit integers, I have 2 values that are 8-bit integers, and I'm passing all of this, everything is 8-bit integer, but all of a sudden I get this warning that says it's an int. And that's because the compiler is implicitly converting your mathematical operation up to an integer to handle any weird edge cases. sign conversion. We saw that earlier. So basically, if you have your warnings turned all the way down, this will compile without warnings. It'll just implicitly do the conversions necessary. And as you saw, you can do user conversion operators as well. And this just allows you to make some special class and then have the ability to assign it to a different class via this conversion operator. So now let's talk about explicit type conversions, also known as casts. So the cast that most people first see is a C-style cast. And this is introduced by just having some parentheses around a type and then followed by the variable you want to change it to. So this is going to kind of create conceptually a temporary of a type using the variable. The type can be any valid type, and you can have qualifiers on it. But it kind of overrides the type system by changing the meaning of the bits that that variable represents. And it can fail to compile under some circumstances. So people think of this as like a very blunt hammer to kind of beat at types to get it to change to something. But under certain circumstances, it can fail. And it can be used in a context expert context, but more on that later. And it can cause undefined behavior. This is also considered an operator. So it actually participates in your operator overloading, level 3, and there's a link to that there as well. So what does this kind of look like in practice? Well, it allows you to pretty much do anything you want, especially if you're dealing with pointers. So here, we've got our float. We can kind of use it to clarify that, yes, we're converting that float, truncating that float to an int. But we can also just randomly tell the compiler, I know this is pointing to float memory, but I want to convert it into an A struct. And I know A and B aren't related, but I want to convert it into a pointer to a B. And then for some reason, we can do that stuff down on the bottom, and it'll all compile. You won't get warnings. So the C-style cast is kind of like a Jedi mind trick that you're trying to play on the compiler, right? You have all these types, like they're statically typed, the compiler's checking it, but you're going in there and you're saying, no. I know what that memory is really pointing to. So let's say we've got a tree that has leaves and a car that has a particular model year. And we've got a function that takes a non-const tree and it prunes the leaves. And we've got a function that takes a const car and it just drives it, doesn't change anything. And in our function, we've got a tree that's constant. It's a fake tree. We don't have to prune its leaves. And we've got a Mustang. Well, we want to drive that Mustang, and it's going to print out driving 1982. Nothing weird with that. Like, it's pretty typical to take a non-const thing and pass it into a function that takes something by const. That works. But, well, now we want to trim our tree. Even though it's a fake tree, we want to trim it. Well, the compiler tells us we can't. We throw a cast in there. We're telling the compiler we can. And now, for some reason, we want to drive our tree. So they're not related. We can't do anything with it, but we're going to tell the compiler, yes, go ahead and drive the tree. Well, it's driving 0 because the beginning part is a Boolean. The Boolean might be false, and yeah. And now we're going to prune our Mustang. It's a non-const variable. We're going to cast it to a tree, pass to that prune function, and then let's drive it. It's going to rip off the first part of that integer because we just sent it to false. So there's a lot of weird things you can do, and none of this code generates warnings if you run it. Kind of an aside here, function pointers are types. So you can cast them. They have a very weird syntax for doing these casts, but it allows you to do things like this. So you can have this run function that just takes a random void star pointer. You can have some function that takes an int and prints out a value. And then you can run the function, do a C-style cast to a void star, because that's completely legal. And then inside there, recast it out to a function, and then call, and all of it works. So when Bjarne was designing C++, they were introducing templates and things like that, and we needed a way to make the built-in types work the same way that user types do for use with templates. And they came up with this C++ functional style cast. So it essentially is going to be something to provide parity with the built-in types. So how does that look? So here we've got two different structs. or three different structs, sorry. So we've got our B inherits from A, and then we've got a C that's completely unrelated. And then we've got a function or a templated function that's going to convert from one thing to another thing. So we've got our int I equals 7, and we can call convert to float, and it'll do the appropriate cast, and it'll send it back. This will be the same as if we just did a normal cast, but if you look at the way that convert to function is, it's kind of is a constructor for a float. And what do I mean by that can only use a single word? Well, if we wanted to do a functional style cast to an A star, which we were able to do previously with the C style cast, this actually won't compile. But you can do something like that. And that will compile. That will do the cast in a functional manner. But you can also, again, this is with along like the C style cast, it doesn't really do any type checking or protection. So you can totally convert that A into a completely unrelated type. Or you can convert it to a reference. That stuff works as well. But you'll notice that the type that's being passed in, again, is going to have that extra parameter tacked onto it, the star or the ampersand. And that is going to be substituted for T. So again, having that extra layer between it allows you to have different types of types and their options. So this also is going to participate in operator overloading or operator precedence. It's going to be level 2, so actually this is a little bit higher precedence than the previous C-style cast. So there are some problems with C-style and functional notation. So there's a single notation with multiple meanings. Are you indicating that you're truncating a variable? Are you creating a new variable? Are you calling a function? Is this an argument? Are you totally reinterpreting what the bits mean? Like all of these things are indicated by the exact same syntax. It's error prone because you can do things that you don't really intend to do and it doesn't give you warnings. It's not greppable, so you have no way of searching, well, is this version of an int cast going to be reinterpreting the bits? Is it truncating the bits? What is it doing? So there's no way to determine all the places you're trying to change the meaning. And it makes just the overall grammar just more complicated, the parsing and things like that. So when developing casting for C++, the stated goals were different notations for different tasks. So if I'm just navigating an inheritance hierarchy, I want to have one type of cast I can search for. If I'm completely changing the meaning of a set of bits, I want a different cast. If I want to just indicate that I'm switching between two things, I want a third cast. And those are going to be easily recognized and searchable. But side note, you have to perform all of the operations, even the unsafe ones, that C-style casts allow, because you don't want to have any room below C++ to not allow something to happen. And just eliminate unintended errors like we saw previously. But there was a fifth goal. To make casting less enticing. It's really, really easy to just do paren int paren. It's a lot more work to say static cast int paren value. So that should kind of give you an indication of how they feel about casting. When you do it, you really need to mean it. So C++ has these 4 casting operators. And they're called operators, but they're actually keywords. So these are keywords in the language. There's no header that includes them or anything like that, but they're considered operators, but they do not participate in operator precedence. Because just their syntax, just by design, doesn't need it. All right, let me get a drink of water here real quick. So, static cast. This could be the first go-to cast that you want to go to. So, essentially it tries to find a path from T1 to T2 via either implicit or user-defined conversions, and you cannot remove a const follow qualification. You can add it, but you cannot remove it. So some reasons you may want to use this is clarify an implicit conversion, as we do there with that float, or indicate an intentional truncation, like yes, I realize I'm truncating this variable. So as with that mathematical formula there. Casting between base and derived, so you can cast up and down the inheritance tree. And then also casting between void star and T star. So if you're interoperating with some C handlers or something like that, you can use static cast to go back and forth that way. So what do I mean by finding a way? How does static cast navigate? So here we've got a struct A that has an explicit constructor that takes an int. And we've got a struct E that has a user-defined conversion to an int. And in our main function, we have an E, and we want to static cast to an A. So what ends up happening? How do we navigate this? Well, the first thing the compiler is going to see is we've got this A that takes an integer. So that might be what we want to do. And E can convert to an integer. So all right, so I can go from an E to an integer to an A, and essentially what ends up happening is something like this. So it navigates through your code through seemingly unrelated methods and succeeds for you. So there's a note on how static cast works on inheritance. Now this is mostly prevalent if you're doing a lot of stuff with pointers, and there's some stuff in here I'm going to show that you probably should never do, but it's to prove a point. Okay, so we've got a base 1, base 2, and a derived that derives from both of these classes publicly. And we're going to have this function that's going to compare memory locations via void star pointers. And in our main, we're going to have our derived, and we're going to make a static cast to a base, and we're going to check to see if those pointers are the same. And they are. They're pointing to the exact same memory location. But now, we're going to take that exact same object, and we're going to cast it to base 2. Now, they're all the same object. They all exist together, but the memory location is now different between those two. Well, why is that? It's because when the memory is laid out, the order in which you have those listed as part of your class or struct is going to just have the order that the memory is laid out. So when we have our derived pointer, it's pointing to the beginning of that derived object, just like we'd expect. And we have the base 1 pointer, it's also pointing to the beginning, because that's where the base 1 portion of the object is located. But when we do the base 2 pointer cast, it actually offsets it to where the base 2 portion of the code exists. So what you would have to do is something like this, where you offset your pointer by the size of the base 1 object, and then use that to compare the memory locations. It's not infallible. So I was saying static cast allows you to go up and down the inheritance hierarchy. Well, here we've got our base class that has a base print. We've got our derived class that inherits from base. We also have an other class that inherits from base. But other and derived are in no way related to each other other than through their parent. So if we have a derived and we convert it to a base and we call d and b.f, we see derived because it's a derived object. But we can static cast it to an other. And when we call that, it actually still prints out derived. But we cast it to another, we didn't get an error or warning or anything. And even if we put in a static assert to say, no, this is really an other, right? It still passes because it is an other, because you cast it. Okay, const cast. I know Jason has some comments on const cast. Exactly. Old man shakes fist at cloud. So this removes our adds const or volatile qualifiers to a variable, but you cannot change the type. The key takeaway here is this does not change the CV qualification of the original variable that you're casting. So here we've got a function that takes a int pointer, but it just uses it, doesn't change anything. We've got a second function that takes an int pointer, but it modifies it. And in our main, we've got our const int I equals 7. So when we go to use that pointer, basically, the use pointer function is just not const correct. It doesn't do any modification, so we can safely cast away that const from the int because it's not going to be modified. And it's going to do what you would expect it to do. But if we do the exact same thing to the modified pointer, since the underlying variable that we're casting the const away from is in fact const, the compiler is completely free to ignore it. So it can cast away the const and everything like that, but when it comes back out, it's not going to be modified. But it can go the other way too. So here we've got a modifiable int j, and we're going to set it to a const int pointer. And we're going to pass it to the modify, and we're going to cast away the const. But because the underlying variable j was modifiable, it's going to modify it and work as expected. So the key with const cast is, remember, it may make the compiler be quiet, but it's not going to actually do what you want it to do in most cases. So here's an example of where const used to be recommended. This is kind of a way I think Scott Myers recommended in his book. So it's used to prevent duplication in member code. So here we've got you're making your own array, right? And you want everything to be const qualified correctly and stuff, so you make a const member function, and we can access the array and everything like that. But then you want to go and you want to make a modifiable array. So, well, this function is not going to compile because the array is modifiable, so we just go in, and now we've got duplicate code. And you can imagine this being much more complicated, where some checks and things like that, but the idea is behind here. So what you can do is you can take your const member function and use it in the non-const context, because remember, your original variable that you're sending to this const cast, so that this pointer that's going to call this overload is itself not const. So you can safely add and remove const to that because the original variable was not const. Okay, brief. This could be in a completely different talk, but I'm going to kind of briefly go runtime type information. This is some extra information that the compiler can add to your code. Can you just hold those questions at the end, please? Thank you. This could be some extra information that the compiler can add to your code for each polymorphic type in the system. This is going to allow the compiler to kind of query what's going on at runtime, whether your types are in the same hierarchy and things like that. And a key thing to note is that this can be disabled. And a lot of like low memory systems, embedded systems, things like that, do actually disable this. But we actually do have it enabled, and we're writing code for watches. So it can be put in embedded systems if you need to. So the reason I mentioned RTTI is dynamic cast, which is going to require this in order to do its work. So what this is this is kind of a way to see if to or from are in the same public inheritance hierarchy as each other. Now, if there's private inheritance, this will fail. You can only cast to and from a reference or a pointer. So if you're doing regular types in dynamic cast, it's not going to work. Again, you cannot remove CV. The thing you're casting to must actually be polymorphic. So if it doesn't inherit from anything, there's no inheritance hierarchy to traverse, so it's not going to compile. Requires RTTI. The way systems without RTTI handle it is going to vary based on the compiler. And if you're casting to a pointer, it returns null pointer, and if you're casting to a reference, it throws a bad cast operation. So here's just kind of a quick, like we've got multiple structs, we can load them into a vector using the base pointer, and we can iterate through the list and try and do a dynamic cast. And if it's null pointer, it skips it. If it's not, that means it actually is of that type. So you can see that the printout is there. So where would that be useful? An example is in a UI framework. So here we've got a widget, and both a label and a button, and they both inherit from the widget base class. And we've got a page that has a whole bunch of widgets, and you want to be able to retrieve these widgets based on some type of ID to be able to perform some action on them. So you've got a page, and when someone touches the screen, it's going to give you the ID of whatever widget was touched. And if someone touches a label, you don't necessarily want to do anything. But if someone touches a button, you want to treat it like a click. So here we can call that getWidget, check to see if it's a null pointer. And if it is, then we just don't do anything. But if it isn't, we can call the click. So we can use the dynamic cast here to navigate that hierarchy. But be wary, because dynamic cast can be expensive. You don't want to just use this all over the place. If you can static cast up and down, static cast up and down. It's going to be much quicker. This is just a portion of GCC's RTTI.c, how they go through and do their build dynamic casts. So, and there's function calls in and out of here and different structs and stuff. So something to keep in mind if you're using this. Reinterpret cast. I know in Herb's keynote he mentioned that you shouldn't be using it, and if you do, it's up to you. But this is essentially the closest thing to a C-style cast. This can change any pointer or any reference type to any other pointer or any reference type. This may also be called type punning. You might hear it called that. This cannot be used in a const expert context. It cannot remove CV qualification. And one big catch is that it does not ensure that the sizes of the things that you're casting between are the same, and we'll get to that in a second. But one place where this is super useful is for memory mapped functionality, especially in embedded systems. So here, if there's some like LED or something that you need to write to in order to, at a certain address, in order to turn it on and off, this is the way to do it. And unfortunately, you can't do that in a const expert context, so this is always going to be a reinterpret cast. Reinterpret cast allows you to do some weird things. So here we have private inheritance. Now again, when we were talking about dynamic cast, if you tried to dynamic cast to a private base class, it would fail. But here with reinterpret cast, you can actually reinterpret cast to a private base class and it'll do the appropriate thing. So not that you should ever want to do this, but you can. So the reason I mentioned the whole size thing is because there's a thing called type aliasing. And again, this can be a complete talk in and of itself. That tiny URL there is from a blog post I found on Gist, where they go into just detailed examples. It's a really good post. I recommend checking it out. But basically, it's just you're trying to turn the memory layouts between each other, and as long as they're compatible. So an example of a compatible, so we've got a struct point that has int x and int y, location, int x and int y, and we can cast back and forth between those using reinterpret cast because their memory layout is exactly the same. The meaning of the memory is exactly the same. Incompatible types are things like this. That's where in the beginning when we saw those casts that things reinterpret the bytes different ways. And this is incompatible. Like the memory layout of a float is not the same as the memory layout of an int. So audience poll, who thinks these are compatible types? It depends. If you have one and you're reinterpreting back and forth, this is kind of like navigating an inheritance hierarchy in C. So you get kind of what you would expect. But if you had an array of these things, well, now all of a sudden you're indexing into incorrect territory. So bottom line, be very careful with reinterpret cast. And I promised I would show you this, how C-style casts are really performed. So under the covers, this is what's going on when you do your C-style cast in C++. So first thing it's going to try and do is get rid of const. And if it matches all of the rules in the system, it's going to select and try and compile. And the reason I say it doesn't succeed is because the compilation may fail. And that's a valid outcome of this tree. But if that doesn't match the right rules, then it's going to try doing a static cast, see if that matches. If it doesn't, it's going to try doing a static cast with const, because it's maybe you're removing const from it, even though you shouldn't be. But it's going to try and static cast const to your type and then remove the const. Failing that, it's going to do your reinterpret cast. And then failing that, it's going to const reinterpret cast and then try and remove the const. And if none of those succeed, you get an error invalid cast. Okay. Oh, we're going to finish up a little early. That's kind of cool. So this is just a selection of additional cast-like things that C++ offers. There's a bunch of other stuff. You've got your get, your anycast, pretty much the entire type traits header is going to have things that are cast-like. But I'm just going to kind of go into these 5 because I found them the most interesting. A bit cast. Earlier there was a talk on const expr all the things, no seriously all the things. And a question came up about bit cast and whether you can do that in a const expr context. So we'll talk about that in a second. But so bit cast is going to be located in the bit header. It's actually a library function, not a built-in cast. And it can convert from into a bit representation of 2. And one of the cool things is that it's going to require that to and from be of the exact same size. So if you try and cast, like you see there, struct C is a different size than struct A and B. So you can't, the bit cast is actually going to fail to compile because they're not the same size. But for something like A and B there, even though that their memory is incompatible, they are the same size, so it'll allow you to essentially reinterpret the bits without having to deal with that type aliasing. Well, without having to deal with the indexing portion of the type aliasing rule. And the same thing goes down with the float and int. You can do it with built-in types as well. Now, this can be used in a const expert contest, as long as to and from are both not or do not contain a union, a pointer to member, volatile qualified type, or have a non-static data member of reference type. So the question initially was, can you bit cast between pointers of two types? Yes, you can, because pointers are the same size, but you can't really do much with it because it's just a memory location. This also can introduce UB if you do something like that float there, and it requires C++20 to do. If you don't have C++20 or you're using C, the canonical way to go about doing this is to use a mem copy. You do not want to use a cast to go back and forth between, even in C, because you can run into that type aliasing rule. Stood move and stood move no except. This again has many talks that go way deep into it, but this converts named variables L values into unnamed variables R values. If present, it's going to call the move constructor of 2, and if not, it's going to call the copy constructor. One thing to keep in mind, a lot of people will first start using like unique pointers and moves like that. Do not return stood move of a variable, because you might run into some return value optimization problems. So just always return the variable straight up. It's an equivalent, it's actually a synonym for static cast tref of var. So you can really do that instead of a move, and it will accomplish the exact same end goal. So move if no except just extends on that. It has a little bit of extra protection on top of it. So if you don't have your move constructor, so if here, if unique pointers move constructor, if the person's move constructor is not marked no except, it will actually fail, or actually trigger the copy constructor if the destination is not marked no except. Stood forward. This is mostly useful if you're doing templating, forwarding and stuff. It's going to just forward on the R-valuedness or L-valuedness of the type, because what ends up happening, and again, this could be another talk, is the pointers and types kind of decay to different values based on what you're passing. But here we've got a templated function that's going to take an R-value reference argument, and we're going to print whether it was, we're going to print out if it's when it's forwarded, and we're going to print it out just when it's passed. And we've got two different overloads of f. One's going to take an R-value reference, and one's just going to take a reference. So if we call it with an R-value, and we forward it, it's going to actually call the R-value function. If we call it with just the regular f function, it's going to convert it into a named variable, and it's going to call the other function. And if we call it with a named variable, both of them are going to forward to the L-value function because they are both L values. As const. So remember back when we had that example of using the const version of, or the non-const version of our array indexer? You can do something like this instead. It's essentially a less verbose way of doing that static cast const t variable, of adding const to something. So here we've got our non-const s.f, and if we assume this was like a vector iterator, really long type, it'd be a lot easier to say as const, and it's going to do the appropriate thing. To underlying. So we are way ahead of time. To underlying. So this is going to be as proposed for C++23, and I'm a huge proponent of using scoped and sized enums wherever possible. It's going to convey a lot more meaning to your code when you're going through and reviewing the code and reading the code and trying to figure out what something's doing. So the more you can use these scoped enums, the better. The problem with that is that when you're serializing this data and you need to convert back and forth between integers and things like that, you've got these static casts all over the place trying to determine what's the numeric value of all of these enumeration values. And it just kind of becomes cumbersome, and there's a lot of extra work there. Because it's essentially equivalent to that static cast there, if you do it appropriately. So by having the as, or to underlying in the standard, it'll allow us to do something like this, where you can do the to underlying, it'll get the appropriate number, and it'll pass it out. So, which cast to use? So, when you are faced with some code and you have a warning, ask yourself this: can I use the correct type and not cast? Do it. Change the types, don't cast. It's going to generate less assembly instructions. It's going to make the code more correct. It's going to make it easier to read. There's just so many different things that it's going to improve in your code base if you can change the type. But I understand you can't always do that. So if you can't, reach for static cast. The key with this, though, is that you know the original variable type, because you want to avoid those instances when you're casting up and down a hierarchy and the types don't match, because this will let you do it. So if you don't know what the original type is, reach for dynamic cast. So if you don't know the variable, you want to check to see, well, is this a label or a button? I don't know. Use dynamic cast, but always check for null pointer and stood bad cast. Because the only time you ever want to use dynamic cast is when you don't know. And if you don't know, you might fail. So you should never have any unguarded dynamic casts in your code. Is my original variable modifiable, or is it const and won't be modified? Use const cast then and only then. The most valid way I can feel to use const cast now is if you're dealing with a CAPI, the CAPI is not const correct, and you know for a fact that that underlying CAPI is not going to modify your variable. So be very, very sure when you're using const cast. And then for adding const, you can just use as const. Do I want to examine the bits of a type using a different type at the same size? Sometimes you need to kind of look through the bits and see what's going on and move back and forth between different struct types based on what you're currently doing. You can use that using bitcast for C++20. And as a last resort, all else fails, or you're in embedded systems and need to write to a predefined memory location. Use reinterpret cast. Use it very, very sparingly. You need to really, if you see reinterpret cast in a commit, you need to be very skeptical about what's going on there. And if all of you saw Herb's keynote a couple days ago, casting isn't dead. Even though, way back in the beginning, they wanted to banish the cast and get rid of it entirely, but yet had to keep it around. The pattern matching is and as is very similar to the casting syntax we've been talking at previously. So it's just going to be kind of moving forward. You can kind of think of is as like a type of dynamic cast, where it's checking to see is something a dynamic cast or not. And you think of as more like your static cast, where it's saying, take a float as an integer, or an A as a B, or base as a derived, or something like that. So casting's not dead. It's moving forward with possibly a much cleaner syntax as well. Some resources. There's the Design and Evolution of C++, which, yes, is out of print, but if you really want it, you can find it. And then one thing that really helped me understand all of the weirdness with all of the built-in C++ style casts is Scott Meyer's Effective C++. He has a nice chapter where he goes over all of the different uses of these casts. And that's really when I first started to understand how all of these casts worked. So with that, I am 20 minutes early. So anyone have any questions? If you're in there working with the code and you're in there modifying it, clean it up. If it's working and you're not touching it, probably not. It's doing what it's supposed to do. Online question?
So const cast is just used to be able to pass to things which expect a non-const parameter. Are there other common use cases of const cast?
The code duplication one for if you have a const version of a function that's a member function and a non-const, and they do the exact same thing, you can use it to forward the const to the const from the non-const. That's one canonical way to do it, and that's, like I said, what Scott Meyer's book says. But really, in that instance, you'd want to use an as const, and then, or wait, no, you wouldn't use static cast, never mind. And that's one way of doing it. And then the other way of doing it would be, yes, the passing to a C function. But other than that, there's really not many good ways that I can think of doing it. Jason.
Just a comment to dovetail off of that one. The deducing this, which has been accepted for C++23, eliminates the use cases for constant casta identifiers.
Yes, I haven't looked into that. The comment was the deducing this will actually eliminate the need for that const cast in that situation that I said. Ben Dean is actually giving a talk on that. When? Tomorrow. Next door, I think, actually. Yes. Oh, in Aurora? Oh, okay. Yeah, so back over there. But yes, so if you're curious about that.
I've heard of I think it's a GSL narrowcast. I don't know if that's being added to the standard or not, but what is the right way of doing the intentional narrowing? Is it a static cast?
So the statement was there is a GSL narrowcast. It's essential. I'm not 100% familiar with how they implement it, but at least based on the built-in casts, the static cast is the appropriate way to indicate intentional narrowing.
I can actually follow up on that. Narrowcast is a static cast, and it helps to make it graphical.
So
what the intent of the static cast is, because it does so many things.
okay, so the comment was that yes, it is a static cast, and it actually adheres to Bjarne's make things greppable. So it indicates intentional narrowing. It allows you to grep for intentional narrowing. Online question?
Does adding final to inherited classes impact performance of dynamic cast?
Say one more time.
Does adding final to inherited classes impact performance of dynamic cast?
Final. Just adding final to inheriting classes. I don't believe it should, because it's just using it to go up the inheritance tree. So if you're on a leaf node and you're final, you can't go down, but you can go up still. So
If you were up and use dynamic cast to go down to something that does have final declared on a virtual member, then it might possibly.
I don't know. It may possibly, I guess was the comment, but I don't know. We could throw it in a Godbolt and find out. Question from online again.
Do you believe that excessive casting damages the value of C++ as statically typed?
Do I believe that static casting is what of C++ is statically typed?
That excessive casting damages the value of C++ as statically typed.
Yeah, I mean, it demonstrates, well, excessive casting is a code smell. So if you see excessive casting, you probably need to rearrange your code to do less casting. But yes, I mean, that is kind of the point of the casting and the type system in C++ is to ensure that the types mean what they say they mean. So that when you're saying that this is an int, it is an int. But if you're casting it, you're changing the meaning of what that thing is. So, but I would argue that if you do have excessive casts, you might need to re-examine your types. Yeah.
With casts that rely on objects being the same size,
Mm-hmm.
do you run into problems when changing platforms like alignment?
Yeah, so the question is when you're using reinterpret cast to swap back and forth between things that are the same size, do you run into alignment issues with different systems and stuff? You can run into alignment issues within the same system, depending on the types and the alignment packing of the structs and things like that. So again, it's another one of those things when you use reinterpret cast, you better really know what you're doing. Like a good example of when we kind of use reinterpret cast is like you're reading just like a buffer from some port or something like that, and it's just going to come in as a bunch of bytes. Well, you can reinterpret cast that buffer into whatever struct type you want. And a lot of times you'll see all of those doing a pragma pack 1 so that everything's just tightly aligned and every byte is lined up. So that's one of the more canonical ways where you would do that type of thing. But yeah, if you don't have everything packed and you have like misaligned variables, yeah, you can totally mess up with padding. Anyone else? All right, awesome. Well, go catch the end of some other talks. You got 15 minutes. So, all right, thanks everybody.